On an aircraft wing, because the pressure above is lower than atmospheric pressure, the surrounding air will tend to blow in. So if you're near the edge of the wing, near the wing tip, it tends to be inefficient. In fact, in a commercial airliner, about the outer 20% of a wing produces very little lift unless it has the winglets, those little things that stick up vertically. This also has to do with the projection of the wing into the body of the aircraft. For there to be effective lift, even under rotation, under compressible flow, forming a vortex above the body of the aircraft, there still must be protection against high pressure air from blowing in. And so it's only the part of the wing that is essentially protected by the wing and the wing root that will produce lift over the body. This is why the projection of the wing is from the shape of the wing towards the center line of the body. The belief that 9 Gs is the current design limit for a fighter plane is incorrect. The correct current answer is probably between 12 and 13 Gs before structural limitations occur. If structural materials improve, that could be raised in the future, but still it makes sense to separate into two pieces, which allows for a much higher level of performance at high-speed flight. One of the key advantages to a higher than 9G turning is the ability to avoid air-to-air missiles. Air-to-air missiles are currently called high probability of intercept for 9G fighters. The fighter plane turns, the missile then pursues and attempts to intercept the fighter plane. The missiles can actually turn at 12 Gs, but they're flying much faster. The turning radius is v squared divided by acceleration. The missiles can actually turn at 12 Gs, but because they're turning so much faster, they actually have a much larger turning radius. Consequently, what they're using is their reaction time. A missile can respond much faster than a fighter pilot can begin the turn of his plane. If you then increase to a 12G fighter, the fighter can turn so quickly that the missile cannot follow and cannot intercept. In order to increase the turning rate of the missile, the winglets on the missile have to be increased in size. This adds aerodynamic drag and weight. It also means the fuselage of the missile must be built heavier. The only place all this weight can come from is the actual weight of fuel on board the missile. So you have higher drag and less fuel. That means that in order to accelerate from fighter plane to its maximum speed, it must burn fuel faster. Current designs of missiles mean that for about 60% of their range, they are actually gliding. An air-to-air missile accelerates from the fighter plane, achieves its maximum rate of speed, flies along that maximum rate of speed, and then when it's out of fuel, uses its momentum to further allow it to travel forward. The momentum portion of its flight is about 60% of its range. If you have to increase its wing area, the winglet area on the missile, this is going to increase drag, plus it has less fuel to burn and it's using more fuel to maintain its velocity. All of this results in a significantly reduced range. In addition, the missile will have to have a higher terminal velocity in order to maneuver to pursue the 12G fighter. All of this reduces the missile's range. The whole theory of a stealth fighter is that it remains outside and fires missiles in. That's not going to be true. A stealth fighter will have to come in and fight, and it will die. One of the other major advantages of building an aircraft in this form is that you get a very large internal wing area, which can produce enormous internal fuel tanks. So there's less need to carry external fuel. The one issue, though, is the need to control weight in actual air-to-air combat. It might be necessary to have a blowdown bottle, basically a compressed nitrogen tank, that can blow compressed nitrogen into the fuel tank and blow the fuel out so that there is not excessive weight for air-to-air maneuvering. Another consideration is power of maneuver. In order for an aircraft to maneuver, it has to use energy. It takes more energy to turn than to fly in a straight line. If the energy is not replaced by the power from the engines, the aircraft will slow down. So if an aircraft can turn at 12 Gs, the next question is how many times can it do this before it slows down and loses maneuverability. The F-35 is designed to have a high slew rate and roll rate. Slew rate is the ability to take the forward direction of the airplane and swing it to either the left or the right. Roll rate is the ability to pick up one wing relative to the other and rotate it. The high G aircraft, because it would have very stiff wings, should be able to achieve very high rates of both and should be superior to the F-35. The vertical stabilizer on a fighter plane is intended to keep the forward direction stable. It is built large for two purposes. One is for low-speed flight, and the second is for when the aircraft body has rotated and the flow from the aircraft body obstructs the flow over the vertical stabilizer itself. By moving them underneath the body, when the aircraft rotates upwards, there would be no obstructed flow, and they can be made much smaller. Under negative G, as the nose rotates down, there might be a need to have additional stabilizers fitted to the top of the fuselage. In terms of velocity, the air pressure increases as v squared times another factor, which is called Prandtl-Glauert, which can give you up to 50% additional bonus times the v squared. Owing to the fact that a fighter plane is taking off at maybe 150 miles per hour, whereas the operational speed is well over 400 miles per hour, if one only wants high-speed flight, the size of the vertical stabilizer can be greatly reduced. For takeoffs and landings, a lifting wing would be needed. It would have booms that would extend from its main wing to a forward wing area. Inside the booms would be included the landing gear. By removing the landing gear from the fighter plane, you can save about 1,000 pounds of weight, plus additional weight needed for the structure of attaching the landing gear. All of this can then be used for additional structure in the aircraft wings and for other structural strength as is necessary. For takeoffs, one would want the total weight, the center of gravity of the combined fighter and lifting wing to be as close to a rear set of landing gear as possible. This would allow the forward lifting plane to achieve a leverage to rotate the aircraft, allowing the main wings then to achieve lift. The landing gear would be in two booms and would include a four-piece set of landing gear, a four-place landing gear. The forward wheels on the landing gear would have to be controlled to prevent a supermarket shopping cart effect of its shimmying while taking off and landing. In order to minimize the amount of storage space necessary for the landing gear would be hinged in the middle and would fold for storage. The rear landing gear, when opened, would form into a straight strut. The forward landing gear would need to have a much longer extension. If the distance from the front to the rear landing gear is 30 feet and 15 degrees angle of rotation is desired, the front landing gear would have to extend 8 feet. The best way to achieve this is by using a grasshopper leg front landing gear that can extend and contract through large directions, through large distances. The lifting wing would be built with the outer parts of its wings capable of folding downwards to save storage space. In addition, the front end of the booms could also be hinged and also made to fold down. This would allow for them to fit more easily into aircraft shelters, as well as just to save parking space. The lifting wing and fighter would be connected through a boom that would look similar to an aircraft refueling boom, but it would have three hinges, one at the body of the lifting wing, one halfway down, and one just above where it connects with the fighter plane. A cable would be attached from the hinge just above the fighter plane to the fuselage of the lifting wing. This is because trying to achieve lift through the boom itself through hydraulics or other systems would not be very practical. The cable would be necessary to lift the dead weight of the fighter plane if necessary. The pilot would position his fighter in position near the boom, and then the boom would connect by using a laser system to identify the connection point. If this fails, the pilot would have to fly his plane with one hand and make the connection using essentially a Wi-Fi TV screen with the other. The boom itself, when connected, would have two trunnions, large metal pins that would come in from either side to lock it with the fighter plane. It should be possible, when this occurs, to still have enough room for a fuel pipe to be traveled down the boom and to the fighter plane. It would, of course, have to have a good seal at the bottom, but this would allow fuel to be transferred from the boom to the plane. It would also allow the lifting wing to be used as a robotic tanker for forward air refueling. When the fighter plane is moved in position against the lifting wing, struts and bumpers would be used to further position it. The struts would enable the thrust from the fighter plane's engines to be transmitted into the airframe of the lifting wing without causing undue rotations or instabilities, as the fighter plane is only hanging on the boom. The bumpers would also allow it to be held firmly and securely in position. In aircraft and other airframe design, the aerodynamic center, always wants to be in back of the center of mass. This is so that if it deflects, the net force will straighten out its flight. If the aerodynamic center is in front of the center of mass, it will actually cause it to spin. Because of this, one wants to reduce the total area forward of any aircraft. For the lifting wing, ideally the forward boom should be thinned out as long as they are structurally strong enough to support the lift from the forward wing. This would then move the aerodynamic center back further along the aircraft and help to stabilize it. Within the booms, the space between the two landing gear sections could be used as large fuel tanks. This would enable very long-range flight in a combined aircraft, or it could allow the lifting wing to be used as a robotic tanker to refuel several aircraft. For maintenance, when the two aircraft set, the lifting wing and the fighter plane, are parked on the ground, a cart would slide in underneath and physically pick up the weight of the fighter plane. The boom can then be separated and maintenance can then be performed on both aircraft. If they would be necessary to be completely separated for maintenance, a heavy vehicle would have to come along and actually grab onto the front end of the lifting wing to prevent it from falling over. The rear landing gear would then be lifted and the fighter plane would be extracted to the rear. The other factor in exceeding 9 Gs in flight is having the pilot maintain consciousness. What happens is that blood, under the increased force of acceleration, is pulled from the brain and drains down into the legs. The one way of stopping this is to put the pilot in a water-filled suit. The suit would look something like an astronaut suit with a scuba diver's hood on top. It would be in two sections. The pilot would climb into the suit. The upper section would be placed, and it would be sealed. The pilot would then climb into his cockpit, and the suit would be filled with water. The water would maintain pressure outside the legs, which would prevent blood from draining down into them and allow the pilot to maintain consciousness. A device similar to this was tested at a place called the Naval Air Warfare Center in Warminster, Pennsylvania in the 1960s. It was an aluminum case, and they spun test subjects at up to 32 Gs without them losing consciousness. For some reason, they never tried to build a suit out of it. The actual controls for the aircraft could be placed into the glove with pressure pads that produce electrical signals. The hand of the pilot would then be placed around a neutral post. The pilot's arm could be in an armrest, and the additional weight from the water in the suit would not require the pilot to move his arm. The pilot can then use things such as texting on the finger pads to actually send signals to his plane or to other aircraft, as well as, of course, currently voice-activated commands could also be used. For ejection, the cockpit of the fighter plane should be located ahead of the engine inlets and the wing and structure of the lifting wing. This would enable the pilot to eject clearly. When the fighter pilot has separated the fighter plane from the lifting wing, that of course would cause no problems in ejection. The main problem is when the pilot is extending at the end of the boom. At that point, the pilot would have to unlock from the boom, separate and disentangle the two aircraft, and then be able to eject. At that point, it is extremely hazardous for the pilot.